Welcome back. Now it's time for a crash course in the fundamentals of computer organization and architecture. We begin with an introduction of the components needed to execute the base RISC-V instruction set. Then we quickly introduce the concept of pipelining and the hazards due to dependencies between instructions. If you break up what an instruction needs to do, you find that every instruction can be done in 4 to 5 steps. 1. First, an instruction needs to be fetched from memory. There is no way around that. 2. An instruction will also be decoded. If there are any source operands in registers, these are retrieved in this step. 3. If the instruction needs to do any arithmetic or logic operation, this is done in the 3rd step. Also, address calculations for load store operations or in branch jump operations can be done here. 4. Next is a memory step, which involves accessing memory for load store operations. Obviously, for all other instructions, nothing happens at this step. 5. The last step involves writing back any result from step 3 or 4 to the destination register. Not all instructions, for instance store operations or branches jumps, have anything to write back to the registers. Let's look at each step in what kind of digital electronic structures are needed to implement each step. The most common case is that the processor executes sequential code, one instruction after another. The PC is a register which stores the address to the next instruction to fetch, which is why the Intel terminology IP instruction pointer is appropriate, but PC is so commonly used we stick with that. The things that we need to do in this step is to fetch the instruction pointed to by the PC and then advance the PC to point to the next instruction. The components needed are shown here. The adder is a combinatorial component, meaning that the output of the adder instantly depends on the values of the input. If you haven't taken a course in digital electronics, there are plenty of sources on the internet. The PC, as stated, is however a register, which is a clocked element. It changes value only when the clock signals it. Then the value on the input, to the left in the figure, is stored in the register and fixed for the duration of the clock cycle. Registers or other clocked elements are often denoted with a triangle at the input of the clock signal. The instruction read from the memory is stored in the register, the instruction register, to be used at later steps. In the 2nd step, the instruction in the instruction register is decoded and operands read. The major component here is the register file, which contains the 32 registers specified by the ISI. GPR means General Purpose Register. It has 2 read ports and 1 write port that all can be addressed simultaneously. RS1 is the 5-bit address to the first source register and RS2 for the other. The corresponding value of the registers appear on RD1, RD2. The WA write address port specifies the 5 bits address to the destination register. If the write enabled signal WE is active, then the data on the write data port WD will be written to the destination register at the next clock signal. Now we are ready to see how it works. We can also see the benefit of the fixed format, which is the characteristics of RISC processors, not only RISC-V but also other RISC ISAs like ARM, SPARC, MIPS, etc. The register fields are always the same bit fields in the instruction. For instance, source register 1 is always bits 15 to 19 and therefore these bits go directly to address the register file. The same for RS2, which is specified from bits 20 to 24 and the destination register at bits 7 to 11. Some instructions do not have 2 source registers, but instead an immediate value encoded in the instruction format at bits 20 to 31. These bits go to an IMSELECT component which will perform sign extension or 0 extension to the full 32-bit width. It's perfectly fine that the register RS2 is read even though it might not be used. Later steps will choose either the extended immediate value or the register data value depending on the instruction. The opcode field, bits 0 to 6, and funct3 and funct7 fields will go to a control unit, which is a quite simple piece of logic that will generate the control signals used in the processor. The control signals to be generated for this step are IMCEL, which tells if the immediate field should be sign extended or 0 extended, and WE, which is the write enabled, specifying that the result should be written back to the destination register. Let's now go to the next step. The ALU operation is quite simple. The arithmetic logic unit has two 32-bit inputs and a control which specifies which operation to perform. The same ALU is used for arithmetic logic instructions such as sub or XOR. The multiplexer, or MUX for short, in blue selects which operand, register value or immediate value to use. The control signal is generated by the control unit having opcode and the funct fields as input. The two final steps can be described in one go. If there is a memory operation, load store instruction, then either mem_write or the mem_read signals will be active. If it's a store operation, the instruction is done here. For all other instructions except branches and jumps, which we will deal with later, there is a value to be written back to a register as specified in the second stage. The value written back can either be from the ALU, in which case the memory is not accessed, or the value read from memory. There is a MUX that selects which one of these to be used. We are now ready to put all the stages together. Here we have put all the things we have introduced together, and to make life a little bit more complicated for you, we have added support for branch and jump instructions as well. The opcode and funct fields from the instruction goes to the control unit, not shown here, which generates several control signals shown with red arrows here. Let's go through the data path for a few important instruction categories. First, consider an arithmetic instruction with two source registers and one destination register. Here we have an add instruction adding x4 with x5 to register x3. The PC addresses the instruction memory. The RS1 and RS2 fields of the instruction are read and will retrieve the operands from the register file, and the op2 cell MUX will select the RD2 operand for the ALU. The data memory is bypassed, and the WB cell MUX will select the output from the ALU to be written back as specified by the reg_write_n signal at the top. Now consider instead a store instruction. Instead of source register 2 being one of the operands, the immediate field is selected and sign extended. The ALU adds the RD1 with the immediate value and uses that as an address to memory. The register source 2 is still read, and this value bypasses the ALU and goes to the data port to the data memory and written. The control unit activates the mem_write signal and deactivates the reg_write_n signal. The final example here is a branch instruction. Consider the instruction BEQ X3 X4 label. This will compare registers X3 and X4, and if they are equal, transfer control to position label. In the instruction, label is represented as the distance in memory from the destination to the address of the branch instruction. Now pay attention, because there is a lot of things going on. Both source registers are read because they are needed for the condition evaluation. The values go to branch logic, which is a box that basically is a simple ALU which can do comparisons and tell if a value is greater or smaller than another. The result will in turn guide the blue MUX at the top, which selects the value of the new PC. Should it be the next instruction in sequence, PC +4, or should it be the branch target, which is calculated in the add unit above the ALU? This one takes the current PC address of the branch and adds it to the immediate value from the instruction. Phew, I think it might be time for a pause now. This table shows the logic for how to set the control signals, which can be seen as columns, based on which instruction that is executed. Different instructions have different opcodes and funct fields, so for example, an ALU operation needs to set op2 cell, the MUX that selects operands to ALU, to use the register value, and no, not the immediate value. It also sets the reg_write_n or RFWEN to enable write-back of the result, and that the write-back should come from the ALU and not from memory. Finally, next PC is taken from PC +4. Consider instead a conditional branch where the branch condition is evaluated to be taken. Its sign extends the immediate, imself control signal, and since the branch condition is evaluated in a separate logic, it doesn't care what we send to the ALU. Important is that the memWrite, regWriteN fields are negative so that any state is not changed. And finally, next PC is selected to be the calculated value from the branch address and the offset.